All right, greetings, scholars. We're continuing our discussion or exploration of Chapter 3 on functions. And here we're going to be working on Section 3.3, Rates of Change and Behavior of Graphs. So some learning objectives. In this section, you will find the average rate of change of a function. Use a graph to determine where a function is increasing, decreasing, or constant. Use a graph to locate the local maxima and local minima. Use a graph to locate the absolute maximum and absolute minimum. So rate of change describes how an output quantity changes relative to the change in the input quantity. The units on a rate of change are output units per input units. The average rate of change between two input values is the total change of the function value's output divided by the change in the input values, right? So rate of change is really slope. So it's like finding the slope between 2 points, which is your change in y. Let me see. Which is our change in y over change in x. So the change in y over the change in x. Another way we articulate this is y2 minus y1 over x2 minus x1, right? Okay, so let's see if we can see this in action. So here it says, using the data in table 1, find the average rate of change of the price of gasoline between 2007 and 2009. Let me mark those. So 2007 is here. 2009 is here. Okay. So if it wants the average rate of change, essentially it's just action for the slope between those 2 points. So let me first list out the ordered pair that's given. So we're looking at what, 2007, and the corresponding output is 2.84. And then we also have 2009, and the corresponding output is 2.41. Okay. So whenever I have an ordered pair like this, even though I know it's like Y and C, I generally just like to automatically label it X1, Y1, X2, Y2, right? Okay. And then the average rate of change is essentially the slope. And so I'm going to use my Y2 minus Y1 over X2 minus X1. So average rate of change is the slope. So then I'm going to plug in the corresponding components. I don't think we have any negatives to worry about here. So my y2 in this case is going to be 2.41 minus 2.84 over 2009 minus 2007. Okay. Let me see, if that were 50, that would be 34 plus 9, 34, 44, so 43. Negative 43, so negative 0.43. And then on bottom, it looks like we get a positive 2. Let's see. So then negative 0.265. Okay, right here. And let me get a copy of this. Copy. Okay. All right. So this is the result we got. So let's see, how do we do? 265. Let me see. Negative 0.43 divided. Did I do my? Maybe I did my division improperly. Oops. Let me see, 2, 13, 6, right? Why is it a 2? Siri, what's 0.43 divided by 2?
0.43 divided by 2 is 0.215.
21. Okay, so I did my long division improper. Let me look at this again. I divided by 2 is 2. Oh, duh. Okay, I see what I did wrong. Yeah. Okay. I made a mistake here. So this supposed to be a 1. So then that makes it a 2, right? So I think we got the same thing. Okay. And again, you can use a calculator. I was just practicing some mental math. I got it a little bit wrong. But we got the final result, right? So it's decreasing by 22 cents per year. Okay. So given the function g of t in figure 1, find the average rate of change on the interval from -1 to 2. Okay. So when x is -1, I guess this is fine. When x is -1, the corresponding y looks like it's a 4. And then when x is 2, the corresponding y is 1. Okay. So then again, I like to label x1, y1, x2, y2. And also one of my mentors would say, every time you use a formula, write it down. That constant repetition ingrains it in your memory. So if we want the average rate of change, that's going to slope. So it's going to be y2 minus y1 over x2 minus x1. Okay. So then I'm going to plug in component-wise. My y2 is 1. My y1 is 4. My x2 is 2. My x1 is -1. So notice I started with a blank set of parentheses. That's to help me to keep track of my signs. And we do have a double negative going on here that we need to account for. Okay. So then 1 minus 4 is a -3 over 3. So then it looks like the final result is -1. So the average rate of change between those endpoints is -1. Okay. Okay. I'm going to let that be. So after picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from her home over time. The values are shown in table 2. Find the average speed over the first 6 hours. Okay. Okay. So that's just the rate of change between from the start to the 6 hours, right? Okay. So the first order pair is what, 0, 10. And then after 6 hours, now the order pair is 6, 292. Road trip does sound nice. Let's go ahead and label these x1, y1, x2, y2. We're going to use our formula, y2 minus y1 over x2 minus x1. Again, this is our slope. We don't have any negatives or anything, so I'm going to go 292 minus 10 over 6 minus 0. So what is that? 282? 282 over 6. Let me see. There's 4 there. 42. So this is 7. So is it 47 miles per hour? Her average speed for the first 6. That seems kind of slow. They must be on like a little side street or something. One of those like scenic highways or something. Maybe. Let me see. Miles per hour. Okay, let's see how do we do here. I think that's what we got, right? 47. So her average speed was 47 miles per hour. Because the speed is not constant, the average speed depends on the interval chosen. If we did the interval from 2 to 3, the average speed is 63 miles per hour, right? So sometimes she's going faster, sometimes she's going slower. So then the averages out to this. That's interesting. I am already getting sleepy. And this is like the first of 3 sections I kind of need to go ahead and submit, but you know, I'll probably take a nap after this. I'll get through this, take a nap, and then wake up and then do the next ones. I'll compute the average rate of change, all right? So average rate of change is just a slope between 2 points. So let me see, for instance, when x is 2, 4 minus a half. Hang on, oh my goodness. Gotta turn that off. Oh. I think it's extra loud. Sorry about that. That's a dehumidifier. If you want a project, I've seen this contraption where, so basically what that was is a dehumidifier. And so the contraption is basically a dehumidifier. It pulls the water or the moisture out of the air, but it makes it drinkable. So it's pulling water out of the air, but it's drinkable water. I think there's a device that you can buy right now. I've also seen schematics where people, now the story goes, I haven't confirmed or tried this to verify or deny, to confirm or deny. But the story goes that there's a group of people that's in like the middle of the desert, and they have these like vertical nets, like this fine mesh net, and so basically, as the air passes through the net, water condenses on it and trickles down to the bottom. They collect the water. These nets are like standing vertical, and standing vertical or whatever. And so, as the water condenses on the nets that's in the middle of the desert, they supposedly collect it at the bottom of the nets, and they have drinking water from that. So I do kind of want to try that to see if I can, just how to pull water out of thin air. And then there are a lot of applications that you can actually do with that, from power generation to drinking water, cleaning, gardening. I mean, it's a lot that you can do with it, if it's true, if I can get it to work. So anyway, that just came out of because I have this dehumidifier that was making all that noise. Okay. Compute the average rate of change. So when X is 2, I think I'm going to just use kind of want to use my calculator. Okay, let me see if I can get it to work. I'll put it here. Let me just close these tabs right here. All right, I think that's about right. It's a little bit, can I change the zoom? Nope. I could do it here. Zoom, I want it to be, yeah, kind of like that. That's better. Let me reload and refresh. Okay. So my y equals, I'm going to put x squared minus 1 over x. So x squared minus, and this is a TI-83 plus, minus 1 over x. Okay. And then I'm just going to use that. Let me check it one more time. I think it's good. Okay. So then I'm going to call on that function, variables, y variables, right? You could always pause, rewind to see my keystroke there. When x is 2, I want to find the corresponding y. Okay, we get that. And then when x is 4, what corresponding y is that? Okay, that's what I needed. 3.5 and 15.75. So when x is 2, that's the corresponding y. When x is 4, that's the corresponding y. So then this is going to be, I'm going to label this as my x1, y1, x2, y2, using my slope formula. Okay, I don't have any negatives, so I'm just going to go 15.75 minus 3.5 over 4 minus 2. Okay. I guess I'll just use my calculator for that as well. So I'll say 15.75. Can't type today. Minus 3.5 divided by 2. Oh no. Okay, let's go with that. So then we get 6.125. Okay. Here, let me hit, I'm going to do math as a fraction. 49 over 8. 49 over 8 is good. Yeah. Okay. It says the electrostatic force F measured in newtons between two charged particles can be related to the distance between particles d in centimeters by this formula. Find the average rate of change of force if the distance between the particles is increased from 2 to 6. Okay. So when the distance is 2, the corresponding force looks like it's a half. When the distance is 6 centimeters, the corresponding force 18. So 1 over 18. So then it's kind of a repeat from here on, just different numbers. Let me see. X1, Y1, X2, Y2. Okay. So then it looks like it's a 1 over 18 minus 1/2 over 6 minus 2. Okay. So I think for this one, I'm going to do it in the calculator a little bit different. Let's see. So we got 2 over d squared. 2 over x squared. Okay. And then I want to find the average rate of change as x goes from 2 to 6. So then what I'm going to do, I'm just going to do it like this. Parentheses, I want to call on the function. I'm going to say what? When evaluate the function when x is 6. Minus when that evaluate that function when x is 1. No. When x is 2. Okay, I'm closing off my numerator. Divided by, come on. 6 minus 2. Okay. So I'll just let the calculator do it. Let me hit math as a fraction. So negative 1 over 9. Okay. Copy. Okay. So the average rate of change of the force is negative 1/9 newtons per centimeter. Okay. Let me see. So here we're asked to find the average rate of change of this function on the interval from 0 to a. The answer will be expressed involving a in simplest form. Okay. So let me see. So average rate of change, I'm going to go y2 minus y1 over x2 minus x1. All right. So let me see. So my y2, that's when x is, or when t is a. So when t is a, we're going to have a squared plus 3a plus 1. And then minus when a is 0. When a is 0, the output looks like it's a 1 over a minus 0, which is just going to be a. It looks like these 1's cancel. Okay, we can factor out an a. So this a is going to cancel this guy and one of those. So it looks like we're left with a plus 3. So now we've made the average rate of change as a function of A. So then depending on whatever A we choose, then we can quickly find the average rate of change from the starting point to whatever A we choose. Okay, it looks like we should get this average rate of change is A plus 3. And A plus 3 is correct. This result tells us that the average rate of change in terms of A as t goes from 0 to any other point t equal to A. For example, on the interval from 0 to 5, the average rate of change is going to be 8. Okay. Yeah, I'm definitely going to have to take a nap after this. Like, I don't know, it just hits me. I guess, I don't know, I think it's because I'm like looking down, writing on a tablet. And so because I'm looking down, then, you know, the body follows the head. Wherever the head goes, the body will follow. But then wherever the eyes go, the head is going to follow. So if I'm looking down, then my head goes down, then my body wants to go down, right? So you can take charge. Like, I guess I need to like stand up and write, and that would help it. I'll still be looking down, but not as much. Like, I'll probably do that a little bit later. Okay, let's keep going. We're about halfway, so we are making pretty good time. It's going a lot faster than I anticipated. Here we're asked to find the local minima and local maximum. A function f is increasing on an open interval whenever f of b is greater than f of a for any 2 points. Input values a and b. A function is decreasing on an open interval whenever f of b is less than f of a for any 2 input values a and b in the given interval where b is greater than a. Let me see. Okay, I'm just gonna scrap that. And like when we start working in examples, like I feel like this is easier to visualize in a graphical or picture representation. But basically, function is increasing. Essentially, as we trace the graph from the left to the right, as long as the graph goes up, then we say the function is increasing. Whenever we trace the graph from the left to the right and it goes down, we say the function is decreasing. And then whenever we trace the graph from the left to the right and it stays flat, we say the function is constant over that interval, right? Over the open interval. Okay. So given this function, identify the intervals over which the function is increasing. So as we trace it left to right, we want to find out where is it increasing, right? So initially, the graph is decreasing, it's going down. Now it looks like something happens when x is 1, right? So I'm just going to mark it with a star. So we had a turning point there, increase. There is another change when x is 3 and then when x is 4, right? So it looks like it's increasing as x goes from 1 to 3. It's increasing there. And then it's also increasing as x goes from 4 to infinity. All right. Let me all right, so those intervals, we can capture them. We can do something like, say the function is increasing as x goes from 1 to 3, and that should be the open interval. Like usually, I'm under the impression whenever we do increasing, decreasing, or constant, we should always use parentheses. That way you're guaranteed to always have at least 2 points. Because if we use square brackets, then we might find ourselves on the end point and we won't have a point either to the left or the right. Right, so again, I'm under the impression whenever we're doing increasing, decreasing, or constant, we always use parentheses. And then it's also increasing on the interval as x goes from 4 to infinity. Infinity always uses parentheses, and in this context, the 4 is going to get a parentheses. I guess I'm hungry. My stomach is like singing. I don't remember the last time my stomach sang. And I got food. I don't know. Everything has been weird. Anywho, but I'm glad that it's doing that. That means that I'm like on that verge of it, eating the excess fat. So I kind of need to just kind of push through it a little bit. And then when I can't tolerate it no more, I'll get something to eat. Just to try to burn some fat. But then I'm probably going into starvation mode. It's a lot. Let me just get back on task. Let me see. So in interval notation, we would say that the function appears to be increasing on the open interval from 1 to 3 and 4 to infinity. Notice in this example that we use open intervals, intervals that do not include endpoints, because the function is neither increasing nor decreasing on the endpoints, on those specific values, right? These points are local extrema, two minima and two maxima, right? So again, that confirms that narrative that I was saying, that whenever we're describing increasing, decreasing, and constant, we always use parentheses. Okay. I think I did have one book that tried to use brackets, and I was like, that's not right. But other books, any other book I've used, they would say that, we use parentheses whenever we're doing increasing, decreasing, or constant. We're asked to graph this function. Then use the graph to estimate the local extrema of the function and to determine the intervals over which the function is increasing. We have 2 over x plus x over 3. For something like that, I would probably make a table of values or use some graphing software. So you can choose several values of x and find the corresponding y and then plot those points. Because to graph this by hand is a lot. What we would have to do is get a common denominator, which looks like it would be 3x. And then it's graphing rational functions. So if we were doing this manually and we wanted to be precise, first we would want to find our intercepts, x and y intercepts. Then we would want to find any asymptotes, vertical asymptotes, horizontal asymptotes, or oblique asymptotes, or slant asymptotes. It's the same thing. Then we would want to do a test for symmetry, right? So even, odd, or neither, right? So you might want to do a quick search on how to do a test for symmetry of functions. We will choose a few additional points between and beyond our x-intercepts and our vertical asymptotes, and then we will put all that stuff together to make the image. For the sake of simplicity for right now, I'm just going to use my prepared notes, but I think more reasonable for you all for right now, either make a table of values, choose several values of x, find the corresponding y, and then plot those points together. That's not going to be 100% all the way there, but that'll give you a sense of it. Or you can use a graphing utility. I'm using a CA2 Plus. Another free graphing online graphing utility is desmos.com or geogebra.com. It would take some research on how to use them, right? How to type things in. But those are free online graphing utilities. Again, I'm just going to use my prepared notes for this. So using technology, we find the graph of the function. It appears that there's a low point. So if this is our image, let me see, it asks the local extrema. Okay. So it does look like there's a low point, like right about here. It's like the bottom of a valley almost. It dips down a little bit, somewhere right in here. And then there's a local maxima right about here. Something like that. Okay, it appears that there's a low point between when x is 2 and 3. So right about here. And a mirror image high point between -3 and -2. All right, so that's approximately what we said. I think we're a little bit off, but it's about there, right? So that was a little bit weird. That's why I was like, something like this, a graphing utility would suffice, and then just read the image. Again, we could do it manually, but for this one, that's going to be a bit much. Okay. Most graphing calculators can estimate a local max and mins. So in the 83 Plus, there's a way to do it as well. Okay. So just give that a go. That once you figure something like that out, the hardest part is just figuring out. But once you figure it out, it's something that you can use going forward, and it goes by much quicker. So for the function f whose graph is shown in figure 9, find all the local maxima and minima. So the local max is going to be the peaks of your mountains. The local minimum are going to be the bottom of the valleys. So we have a local max when x is 1, with the corresponding a local maximum value of 2 when x is 1, and then a local minimum value of -2 when x is -1. So again, the local max is going to be the peak, the top of the mountain, and the local minimum is going to be the bottom of the valley. Okay. A local maximum when x is 1, the local maximum value is going to be what, 2 when x is 1. The local minimum value is going to be -2 when x is -1. Okay. Okay, let's keep going. Whew. Yeah. Anyway, let's keep going. We'll now return to our toolkit function and discuss their graphical behavior from figures 10, 11, and 12. Okay, so the toolkits, right? Again, that's where you might hear me call them either your parent functions or your basic functions. So for instance, the first one that we talked about was a constant function. So then where is it increasing or decreasing, right? So if it's constant, it's neither increasing nor is it decreasing anywhere, right? So increasing and decreasing, it doesn't happen. So it's neither increasing nor decreasing. Identity function, this guy here, that's where y equals x. It's always increasing over the entire domain, so over all reals. So as we trace it from the left to the right, it just goes up. So we say it's increasing over the entire domain of all reals. Oh, this is actually fairly short. Oh no, is that not displaying properly? I feel like something is missing there. But yeah, it should be increasing over the entire domain, all reals. Quadratic function, now notice as we trace it from the left to the right, initially it's decreasing. So that's from -infinity up to 0. And then it's increasing from 0 to infinity. And we have a minimum value at the origin when x is 0. Okay. So for the cubic function, as we trace it from the left to the right, it's always increasing over the entire reals. So it's always increasing. The reciprocal function, as we trace it from the left to the right, it's always decreasing. And I don't think there's any max or any min. Let me see. And then I'll do that later. It's decreasing over its domain from -infinity to 0, and then from 0 to infinity. So, and we're using parentheses on all of those because it doesn't reach 0. The reciprocal squared is increasing from -infinity to 0, and then it's decreasing from 0 to infinity. All right, with the open intervals. Okay, and then here, the cube root function is increasing over the entire domain. In this case, it's going to be all reals. Square root is increasing over its domain, which is the open interval from, well, actually, not over its entire domain. It's increasing from 0 to infinity. So not at 0, but from 0 to infinity. So the open interval from 0 to infinity. Absolute value, initially, as we trace it left to right, is decreasing. So it's decreasing from -infinity to 0, the open interval from -infinity to 0. And it's increasing on the open interval from 0 to infinity. Oops, you can see it here. And the thing is so weird. I don't start yawning like this until I sit down to do this work. When I be doing other things, well, I guess I take naps, but it just seems like all of a sudden it always hits me when I sit down to do this stuff. The absolute max of a function at x equals c is going to be f of c that's going to be larger than all y values for all x in the domain. The absolute minimum of f at x equals d is going to be f of d, where it's going to be less than all y values for x in the domain of f. Okay. So local minimum is basically those peaks and those valleys. The peak of the mountain, the bottom of the valley. The difference with local minimum and absolute minimum is the absolute is still the same thing, the peaks and the valleys, but you also have to consider the endpoints. Like you need endpoints. You have to consider the endpoints whenever possible. Okay. So for this function shown in figure 14, find all absolute max and min, right? So the absolute max, if we consider the endpoints as well, wait a minute. Yeah, right? So I think these have the same y value. So those are larger than all the other y values. So we have 2 maxima. The absolute minimum, if we consider, our peaks, our valleys, and the endpoints, out of all those components that have circle, the lowest one is the endpoint. So our absolute minimum is going to be, what is it? -10 when x is 3. Okay. All right. So again, when we're considering absolute max and min, we still identify our peaks and our valleys, and we also consider the endpoints, and then the highest y values are our absolute maximum. The lowest y value are our absolute minimum, right? Let me just write it. Okay. So I'll say the absolute max looks like it's what, 16 when x is what, -2 and 2. And then the absolute minimum value, it looks like it's -10 when x is 3. So the graph attains an absolute maximum value in 2 locations when x is -2 and 2. Because at these locations the graph attains the highest point on the domain of the function, the absolute maximum value is the y coordinate at when x is -2 and 2, which is going to be 16. The graph attains an absolute minimum value when x is 3, because it's the lowest point on the domain of the function of the graph, of the function's graph. The absolute minimum value is the y coordinate at x equals 3, which is -10. I don't like the way they word that. The absolute minimum value is -10 when x is 3, right? So anyway, we have it. It's just the articulation, the way they articulated that was kind of like weird to me. Okay, so with that, we made it through that. I will be making, so that was 3.3. I'll be making the videos for 3.4 and 3.5 shortly. Okay. And so with that, we're going to go ahead and end this session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.